DDR4, mainstream RAM. DDR4, or Double Data Rate 4, is the RAM that's been living in most desktop computers and laptops since around 2014. If you bought a computer in the last decade, there's a good chance this is what's inside. DDR4 memory modules are installed on your motherboard in slots called DIMM slots. DIMM stands for Dual Inline Memory Module. These modules have 288 pins on the bottom, 2 independent rows of connections, 1 on each side. The average motherboard has between 2 and 4 of these slots, depending on how much the manufacturer thought you'd need. Here's how DDR4 actually works. When you open a program or a file, that data needs to move from your hard drive into RAM first. Only then can your processor access it and actually do something with it. RAM is essentially the waiting room between your storage and your processor. The more RAM you have, the more data can sit in that waiting room ready to go, which means your processor isn't constantly running back to the hard drive like a frustrated office worker fetching files from a basement archive. DDR4 operates using something called double data rate technology. This means it transfers data on both the rising and falling edges of the clock signal. Non-DDR RAM, the older single data rate stuff, only use the rising edge. So even at the same clock speed, DDR4 sends twice the amount of data per cycle compared to older single data rate memory. DDR4 speeds typically range from 2,133 MHz up to around 3,200 MHz for standard modules, though enthusiast kits can push well beyond that. These modules have a 64-bit data path, which translates to an 8-byte wide bus, because 64 divided by 8 equals 8. This bus width determines how much data moves in one cycle. DDR5, next generation RAM. DDR5 is the newer standard that started appearing in consumer systems around 2021. It's not just a speed bump, it's a fundamental redesign of how RAM operates, though it still ends up doing the same job of holding data for your processor. First, the physical differences. DDR5 modules still have 288 pins, the same count as DDR4, but the notch on the bottom is in a different location. This means you cannot accidentally jam a DDR5 stick into a DDR4 slot. Motherboards are built to support one generation or the other, not both. You're picking a side when you buy. DDR5 starts at speeds around 4,800 MHz and scales up to 6,400 MHz and beyond for standard kits. Higher-end overclocked modules are pushing past 8,000 MHz, which is frankly absurd compared to where DDR4 started. But speed alone doesn't tell the whole story. The real improvement is in bandwidth and efficiency. DDR5 uses less power than DDR4 while delivering significantly higher data transfer rates. A DDR5 4800 module, the baseline speed, already outperforms most DDR4 kits. The voltage drops from 1.2 volts in DDR4 down to 1.1 volts in DDR5, which matters for laptops and systems that care about power consumption. DDR5 also changes how the module manages power. Each stick now has onboard power management instead of relying entirely on the motherboard. This allows for better stability, especially when you're running multiple sticks at high speeds. Another upgrade is capacity. DDR5 modules can scale much higher per stick, while DDR4 tops out around 32 GB per module in consumer space. DDR5 can go up to 64 GB or more per stick without breaking a sweat. So if you need massive amounts of RAM for video editing, 3D rendering, or running virtual machines, DDR5 makes that easier without filling every slot on your board. VRAM, or video RAM, is the memory that lives on your graphics card. It's not system RAM. It doesn't sit on your motherboard. It's soldered directly onto the graphics card PCB, right next to the GPU chip, because graphics processors need their own dedicated memory pool to function. The G in GDDR stands for graphics. GDDR5, GDDR6, and GDDR6X are all variations of DDR technology, but they're optimized specifically for the absurd bandwidth demands of rendering images, textures, and frames at high speed. System RAM prioritizes low latency, the time it takes to access data. VRAM prioritizes throughput, the sheer volume of data it can move per second, because graphics workloads are all about moving massive amounts of information quickly. GDDR5 was the standard for years. It appeared in graphics cards from around 2008 through the mid-2000s. It offered bandwidths up to around 336 GB per second on high-end cards, which was enough for 1080p gaming and early 4K attempts. GDDR GDDR6 arrived around 2018 and doubled the bandwidth potential. Modern graphics cards using GDDR6 can push over 600 gigabytes per second of memory bandwidth. This is necessary because rendering at higher resolutions, like 1440p or 4K, with complex textures and effects, requires moving enormous amounts of data every single frame. Then there's GDDR6X, which is essentially GDDR6 on performance-enhancing substances. Developed by Micron, it uses a different signaling method called PAM4 instead of the standard binary signaling. Without getting lost in the technical weeds, PAM4 allows each signal to carry more data, which increases bandwidth even further. High-end graphics cards with GDDR6X can exceed 1000 gigabytes per second of memory bandwidth. The amount of VRAM on a card matters too. Modern games at high settings can easily use 8 to 12 gigabytes of VRAM. If you run out, the card has to start swapping data back to system RAM, which is dramatically slower, and your frame rate collapses. LPDDR, laptop and phone RAM. LPDDR stands for low power double data rate. The LP part is the entire point. This is RAM designed specifically for devices where battery life matters more than raw performance, which means laptops, tablets, and smartphones. The key difference between LPDDR and standard DDR is power consumption. LPDDR memory operates at significantly lower voltages than desktop DDR. LPDDR4, for example, runs at around 1.1 volts, and LPDDR5 drops that even further to around 1.05 volts. Desktop DDR4 runs at 1.2 volts. That difference sounds tiny, but when you're trying to squeeze 10 hours of battery life out of a thin laptop, or keep a phone running all day, every milliwatt counts. LPDDR memory is also physically different. Instead of being installed in removable DIMM slots like desktop RAM, LPDDR is soldered directly onto the device's motherboard. This is why you cannot upgrade the RAM in most modern laptops, and why every smartphone has a fixed amount of memory. It's permanent. You're stuck with whatever the manufacturer decided to install. The benefit of soldering the memory directly is that it takes up less space and uses less power, because the connection between the processor and the RAM is shorter and more efficient. The downside is zero upgradability, which is fantastic for planned obsolescence and incredibly annoying for consumers. LPDDR5, the current standard in high-end phones and laptops, can hit speeds around 6,400 megatransfers per second, which is comparable to DDR5 in terms of raw speed. But again, the priority is efficiency, not performance. LPDDR5 uses about 20% less power than LPDDR4, while delivering better bandwidth. You'll find LPDDR in Ultrabooks, MacBooks, tablets, smartphones, and even some compact desktop systems where space and power are constrained. It's not as fast as desktop DDR5 in real-world performance, but it allows these devices to stay thin, light, and functional for hours without needing a wall outlet every 90 minutes. ECC RAM. ECC stands for Error Correcting Code. This is RAM with a built-in safety net. Standard consumer RAM just stores data and hopes nothing goes wrong. ECC RAM actively checks if the data was stored correctly and can fix errors on the fly before they cause problems. Here's how you can physically identify ECC memory. A standard non-ECC memory module has 8 memory chips on it. An ECC module has 9 chips. That extra chip is dedicated to storing parity data, which is used to detect and correct errors in the other 8 chips. Memory errors happen more often than you'd think. Cosmic rays, electromagnetic interference, voltage fluctuations, and just general weirdness can cause a bit to flip from a 1 to a 0 or vice versa. In your home computer, this might cause a program to crash or a file to corrupt. Annoying, but not catastrophic. In a server handling financial transactions, medical records, or scientific calculations, a single bit error could mean losing money, corrupting patient data, or ruining months of research. That's unacceptable. ECC memory detects these errors and corrects them automatically before they propagate through the system. The server keeps running. The data stays intact. No one even knows an error occurred unless they're checking the logs. The trade-off is performance and cost. ECC RAM is slightly slower than non-ECC because of the overhead required to check and correct data. It's also more expensive because it requires that extra memory chip and specialized controllers on the motherboard. Most consumer motherboards don't even support ECC. You need a workstation or server-class motherboard, and usually a Xeon or ePYC processor to use it. ECC is standard in servers, workstations used for professional work, and any system where uptime and data integrity are critical. For gaming or general consumer use, the performance hit and extra cost aren't worth it. especially since modern RAM is already fairly stable. Registered buffered RAM. Registered RAM, also called buffered RAM, is what happens when you need to install truly absurd amounts of memory in a single system. We're talking servers with 512 gigabytes, 1 terabyte, or even multiple terabytes of RAM. At that scale, standard unbuffered memory simply doesn't work. The problem is electrical signal integrity. When you have a processor trying to communicate with 8 or 12 memory modules simultaneously, the electrical signals start to degrade. It's like trying to have a conversation with 12 people at once while standing in a noisy room. Eventually, the signals get messy, timing gets inconsistent, and the whole system becomes unstable. Registered memory solves this by adding a register, which is essentially a buffer chip between the memory controller and the actual memory chips on the module. This register sits in the middle and cleans up the signals before passing them along. It reduces the electrical load on the memory controller, which allows the system to support more memory modules without everything falling apart. RDIMM stands for Registered Dual Inline Memory Module. These are the standard registered modules used in most servers. They allow systems to run more memory at stable speeds, but they introduce one clock cycle of latency because of that buffer chip sitting in the middle. LRDIMM stands for Load Reduced Dual Inline Memory Module. These take the concept further by adding additional buffers to reduce the electrical load even more. This allows for even higher memory capacities per system, sometimes supporting modules up to 128 gigabytes per stick. The trade-off is slightly higher latency, but when you're building a database server that needs 2 terabytes of RAM, you accept the latency penalty. You will never see registered or load-reduced memory in consumer systems. They're slower, more expensive, and require server-grade motherboards and processors. They exist purely for enterprise environments where memory capacity matters more than raw speed. HBM. HBM stands for High Bandwidth Memory. This is where memory technology starts looking like science fiction. Instead of laying memory chips flat on a circuit board, HBM stacks them vertically like a tiny skyscraper and connects them directly to the processor using an extremely wide data bus. Traditional memory, whether it's DDR5 or GDDR6, has a relatively narrow bus width. A standard DDR5 module has a 64-bit bus per channel. HBM, by comparison, uses a 1024-bit bus per stack. That's 16 times wider. This massive bus width allows HBM to move enormous amounts of data with relatively low clock speeds, which also means lower power consumption compared to GDDR memory running at extreme speeds. HBM uses through-silicon vias, or TSVs, which are tiny vertical connections that pierce through the stacked memory dies. This allows the memory layers to communicate with each other and with the processor below, without requiring long traces across a circuit board. The entire stack sits directly on the same package as the GPU or processor, connected through an interposer layer. The result is bandwidth that makes even GDDR6X look modest. HBM2, which appeared in high-end graphics cards and AI accelerators around 2016, offered bandwidths exceeding 450 gigabytes per second per stack. HBM2E pushed that to over 600 gigabytes per second. HBM3, the current generation, can exceed 800 gigabytes per second per stack, and some configurations push well beyond that. You'll find HBM in professional graphics cards like AMD's Radeon Instinct line, AI training chips, and high-performance computing accelerators. Some consumer graphics cards have used it, but it's expensive to manufacture and requires advanced packaging technology. So most gaming GPUs still use GDDR6 or GDDR6X. HBM is soldered permanently to the GPU package. There's no upgrading it. It's part of the chip itself. But for applications that need maximum memory bandwidth, like training large AI models or running scientific simulations, HBM is currently the best option available. DDR Trice, Legacy RAM. DDR3 is the RAM that dominated computers from around 2007 through the mid-2000s. It's legacy technology now, but millions of systems are still running it, and it's worth understanding because it shows how far memory technology has progressed in a relatively short time. DDR3 modules have 240 pins, the same count as DDR2, but the notch is in a different position to prevent mixing them up. Speeds typically range from 800 MHz up to around 2,133 MHz for higher-end kits. Compared to DDR4, which started at 2,133 MHz, DDR3 topped out where the next generation began. DDR3 operated at 1.5 volts standard, or 1.35 volts for low-voltage variants. DDR4 dropped that to 1.2 volts, and DDR5 is down to 1.1 volts. Each generation reduces power consumption while increasing performance, which is the entire point of moving forward. The maximum practical capacity for DDR3 was around 16 gigabytes per module in consumer systems, though most DDR3 sticks maxed out at 8 gigabytes. If you wanted 32 gigabytes of RAM in a DDR3 system, you needed 4 8-gigabyte sticks, which meant filling every slot on your motherboard. DDR3 is still perfectly functional for basic tasks. Web browsing, office work, and light media consumption don't require cutting-edge memory. But modern games, video editing, 3D rendering, and anything memory-intensive will struggle on DDR3 systems. The bandwidth just isn't there. Many older workstations, budget systems, and refurbished computers still run DDR3. If you're using one, it works, but you're leaving performance on the table. Upgrading to a DDR4 or DDR5 system means not just faster RAM, but also a faster processor, better motherboard features, and support for newer storage technologies. DDR3 served its purpose. It was a solid workhorse for nearly a decade. But technology moves forward whether we're ready or not, and DDR3 is firmly in the rearview mirror now. If you want to understand more tech that's been hiding in plain sight, go check out the video on screen now explaining every USB port color and what they actually mean.